Okay, question number 1 in the drill. 29th today, I think, of the 9th. Ten cubed times 10 squared. What does that become? Sort of leading into today and the laws of indices. From last week, we had that. What do those symbols stand for? What particularly do the M and C stand for? And Y and X, what do we call those? And where do they go on axes? Number 3. Here is a graph that's been plotted. And I've had some points on there. Here they are. And I've drawn the line. If I want to use this graph to predict a value here, given a particular value there, what's the value on that axis? If I want to use that to predict it by extending the line a bit, what do we call that? What word describes that process? Number 4, what's the answer to that? Solve that. Number 5. Which again takes us into today. Number 6. Write that number down in engineering notation. And also, if this was an energy in joules, what would be a suitable prefix? Similarly, if that was a charge in coulombs, write that in engineering notation and also with a suitable prefix. Finally, here are 2 numbers. Using a calculator, find the answer to that, please. I'll pause the video there, so then if you're looking back at it, you can then have a go at it if you use it for revision, and then look at the solutions. Okay, let's have a look. So number 1, 10 cubed, of course, means this. 10 times by itself 3 tens. 10 times 10 times 10. Incidentally, a dot is often used instead of a multiplication symbol. So I times that by 10 squared, which is 10 times 10. Haven't I got 10 multiplied by itself 5 times? So effectively, this turns out to be 10 to the power 5. So, but if you wrote down 100,000, which is the same thing, that would be okay too. But it's highlighting something we're talking about later, which is the laws of indices. This is the first one, where you're multiplying numbers together, you effectively add the powers. So 3 plus 2 equals 5, so long as the base, which is this, is the same. Number 2, y equals mx plus c. Y. Yeah, and what variable do we call that? The dependent variable. Y is a dependent variable, which goes on the y-axis, i.e. the vertical axis, yes. So this must be the independent variable. The one we're controlling, remember. Independent variable, and the y is the one that depends on that. M, the gradient of the line, good. So in this case, that gradient would be given by how far you go up, by how far you go along. Drawing a triangle somewhere convenient. That's the gradient. And lastly, the y-intercept, where it cuts the y-axis here. Number 3, what do we call this process where we are extending the line and then trying to interpret, or guess or predict a result from that? What do we call that? Extrapolation, yes, extrapolation. Can't get it all on. Extrapolation. What about if we try and take it within our range? Interpolation, yeah. That's simple. I deliberately didn't read out what that was, but we would say the square root of 9, which means what number do you multiply by itself to get 9? What's the number which times by itself gives 9? 3, because 3 times 3 is 9. Is there another answer it could be? Minus 3, good. It can, whenever you square root a number, the answer could be either positive or negative. You always get 2 roots. Minus 3 times minus 3 is 9. Plus 3 times plus 3 is 9. So if I'm going back from here to here, I've no idea which one I had to start off with. So you always have to write positive and negative. There's 2 possibilities. Yes and no. It depends on the question. If it's an engineering situation, obviously, sometimes it's obvious, do we want either the positive or the negative root? So it depends on the question. Often we'll ignore one of the roots because it's impossible. So yeah, depends on the question. Number 5, 2x plus 3 equals 11. If I had to solve that, I would use the steps that I'm going to go through now, and we'll be talking more about that later. 2x plus 3 equals 11. However complex it is, you ask yourself the question, what's happened to x to get this left-hand side of the equation? Well, x has been multiplied by 2, and then 3 has been added, is the order, effectively. So to undo that, I go in reverse. The first thing I do is get rid of the 3 by subtracting it. As it's added, I subtract it. So subtracting 3 from both sides, I get that. And then, what's happened to the x? It's been times by 2, so divide by 2. And that cancels that out. But I must divide both sides by 2, so x equals 4. You could pretty well do that by inspection, but it's the steps that's the important thing, because when they get more complex, you need to follow the steps. Next one. Engineering notation. I can move this decimal point back as many times as I like, so long as I go in threes. So 3, 6, 9, I could call that 123 times 10 to the 9. Or I could go back another 3 and call it 0.123 times 10 to the 12, or 123,000 times 10 to the 6. You have a choice. There's no right or wrong answer, but that's probably the most convenient. So I'd call that 123 times 10 to the 9 joules, or 123 gigajoules, because giga is the prefix that means 10 to the 9. Similarly for this one, I can go in threes. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could call it 0.13 times 10 to the minus 9, or 130, putting a 0 there, times 10 to the minus 12. It's often convenient, to write it like this, because if I write 0.13, well, there's no right or wrong answer, but I'd probably stick with this one and call it that. But if you've done it 0.123, that's fine. 10 to the minus 12. Pico, well done. 130 picocoulombs. A useful skill in this last one is to estimate to get your answer before you start, so you've got an idea. You remember what we did at the beginning of this little drill? If I've got times 10 to the 9 multiplied by times 10 to the 6, I add the powers. 9 plus 6 is 15. 32 times 1, roughly, 30 times 1 is around about 30. So I'd expect about 30 times 10 to the 15 if I were doing this on a calculator. But if I do it on the calculator, it's going to give me in standard form, i.e. it's going to put the decimal point after the first significant figure. So it would probably say 3 times 10 to the 16, because I've gone one more place. So you do it on the calculator, and what do you actually get? Somebody. Is that right? Yeah, okay. And then I look at it and round it to an appropriate number of significant figures. And if we look at this, 3 significant figures, 3 significant figures, so in the solution, 3 significant figures. The rule of thumb is the same as the least accurate number that you're given, or maybe one more. So I could go to 4. So I might decide, as that's roughly in the middle, this 6, I might call it 4.406 times 10 to the 16 to 4 significant figures. I put that at the end to tell somebody who's looking at it that I've rounded it. So that's the sort of thing you do when you use your calculator. Estimation isn't a bad idea. At least go as far as adding the powers up. So you've got an idea, something like 10 to the 15, but actually 16 because of where the decimal point is. And then, once you've got your answer, think about rounding to an appropriate number of significant figures.